Okay, so welcome back to the next session. I hope you got a quick coffee and a run around just for that extra 15 minutes. So I hope you enjoyed that point. So you're having some Danish or something as well. That's awesome. I'm going to introduce Salvador, but what I would like to do is I walked past this morning myself, so I'm sure many of you have. From the Dawson Group, there's a leaflet drop on your chairs, and it isn't immediately recognisable what that relates to. But there's a clean room out in the car park. So the invitation from the Dawson Group is that if during one of the breaks you would like to go out and have some fresh air, there's a modular clean room or a clean room out on the car park. It should stand out because everything else will look like a car. And this won't. So if you do have that interest, please go on out and have a walk around the Dawson Group's clean room. That was the ask. Okay, to introduce the next session, as I tried a little earlier, but I've now learned that we have to stay to rules and we have to stay to time today because the app that we're running this on is all very time bound. So introducing Salvador López now from Telstar, continuing with what EECO2 presented just recently on a net carbon target. Salvador is going to present to us on HVAC energy savings in classified areas by using smart cleanroom. So we'll hand over to Salvador to explain what that is. It's a 39-minute presentation. And at the end of it, I hope that we have Salvador, the real Salvador online on screen for Q&A. So again, if you have any questions during the presentation, hold those back and ask them. Or if you're online and virtual, please use the app and put your questions in and we'll put those to Salvador.
Welcome, good morning, ladies and gents, to this new Clean Room Technology Conferences. I couldn't make it to Birmingham this time, but I hope I can explain briefly and correctly the topic of this session. As the title said, we are going to talk about one of the angles of the HVAC energy savings in a pharmaceutical clean room. This is a, let's say, hot topic for the last few years at least, with a big debate on whether it makes sense to keep the fixed air change rates, fixed air change flows in the rooms according to a conventional set of criteria. Let's say class D being from 20 to 30 air change per hour, or class C 30, whatever, so on and so forth. Many of us are, let's say, also working on the more scientific way of fixing these air changes through the fluid dynamic simulations. This is one way where we don't have prefixed air changes, but we set them accordingly to the simulation we make in computer for whatever classification of clean room are. But in this case, we have approached the matter in a different way, more in a practical way. So let's start. First, the agenda will be, a quick introduction of the situation. Then I will make a brief description of the smart clean room, is how we call it. Then we will focus a little bit more in the commission and qualification, which must be or is the more difficult part of this solution. And then I will show some results of a case study that we made already. Sorry, but moving the slides very quickly. A smart clean room is not, let's say, a product. It's not a software. It's not something that you can just buy and install and that's all. Unfortunately, it is something that we have to tailor-made to the users' requirements, to the process requirements, to the, in some cases when we are talking about brownfields, to the current installations. So it's, let's say, a tailor-made flexible solution for the clean rooms, where we will adjust the supply airflow to the clean rooms, considering one of the major parameters of the environment classification, which is the particle counters. Not forgetting, obviously, the other 3 conventional parameters, which are temperature, humidity, and differential pressure among the different rooms. By commanding the supply chain, the air supply, we are able to reduce the energy consumption of the clean rooms and thereafter reduce the operating cost. As I said, it's not just software that you install and forget. It's not something that you have to change in your HVAC. It's a combination of everything that has to be aligned. So typically, it will require an HVAC engineering work. It will involve changes or let's say new materials in mechanical devices and instrumentation. It will have to be considered in the HVAC control system, and obviously it will require some more effort in the startup and in the commissioning and qualification. Very quick market overview. It is said in many paperwork that the HVAC consume around 70% of the total energy consumption of a pharmaceutical facility. Obviously, it depends on where it is located. It depends on what is exactly the process. But as an average, we have this figure, which is not minor. We have additionally a requirement to reduce operating cost, increasing competitiveness. This is a big trend for the last 10, 15 years, and that we have to bear in mind. We had also the component of corporate social responsibility, which every year is more important, especially with the CO2 footprint. We have also this demand of innovative solutions linked probably to Industry 4.0 and other solutions to improve efficiency. We have also the Annex 1, whenever it happens, increasing the requirement of particle counting monitoring in aseptic areas. So a smart clean room has been especially developed for the pharmaceutical industry when working in any other industry. And obviously, we need to meet the latest standards and robustness to ensure compliance with the GMP rules. Okay, let's see if I can move the. Yes, yeah, I can. So let's explain a little bit what we did with the smart clean room. When you are modifying the supply air in the rooms, typically we face perturbances in the pressure drop among the different rooms, and also we may face perturbances in the temperature or humidity control. So as a starting point, changing the supply air is not, let's say, easy. In a conventional mode, normally we have a fixed air change rate, which is what we call the design flow. And typically, you may have used the fluid dynamic simulation, and probably you can already start with a reduced air change. But if not, you will have gone typically to your requirements, where are based in decades of same criteria for Class D, Class C, Class B areas, which are criteria of air change rates based on experience, but not, let's say, optimizing the need of air supply. So this fixed air change, you will control temperature, relative humidity, and obviously differential pressure. You may have some circumstances in your engineering where a room is not commanded by the fixed air change conventional, but is commanded by the energy let's say the energy from the process equipment. So you may have a thermal load requiring bigger air change than the conventional part. In a smart eco mode, what we will have is a kind of variable air change rate. Here, obviously, we still have to consider and control temperature and relative humidity. We still have the differential pressure as a must to be to comply with, and we will be adding the airborne particles measurement. So together with the temperature, humidity, and differential pressure data acquired from the clean rooms, we will have the particle counters consideration. And this will help us to adapt the supply air. We can see it in a different picture. You will have, as always, the supply air in the room. You will have one or several particle counters in the room, depending on the risk assessment we make. We will have the return air and the differential pressure with the surrounding rooms. And you have temperature and humidity. So these will be the 4 parameters acting on the HVAC system. Differential pressure among the different rooms, temperature, relative humidity, and particles, airborne particles in the room. As said, the supply airflow, you cannot change it in one set immediately, because the balance of airflows among the different rooms, that means the balance of the differential pressure at the different rooms, can become absolutely unstable for an unaffordable period of time. So what we design is a rundown time, which 2 parameters that will be fixed during the startup and commissioning, which we will see now. Then we see kind of eco mode, which we call minimum flow, which which also will be set during the startup and commissioning and qualification. We may have pre-calculated this minimum flow, but at the end of the day, we will reach this after the practical trials of the installation itself. And then we may have, or we will have, another parameter, which is the ramp up. Whenever a perturbation happens in the room, particles, temperature, or whatever, we will react immediately to set again all the system in the design flow. What we discovered is that the stability of pressures and temperature and humidity was easier to achieve whenever we were increasing the flow compared to when we are reducing the flow. So this is why the ramp to reach the minimum flow is longer, and the ramp up to recover the conventional flow is quicker. Also, we need to be quicker. Well, this is the same slide explain the let's say 3 stages coming from conventional setup, the decrease of airflow to reach the minimum flow of the installation. Again, we are not talking about a singular room, but several rooms several air handling units, and everything affecting one to the other. We have the reaction time, and then a period of working under conventional conditions. A smart eco mode have obviously a set of initial conditions to start. It will not start if we have any particles airborne alarm in the rooms. So we will keep the conventional situation. It will not start if we have any alarm in the clean rooms or about the differential pressure. It will not start if we don't if we are not getting the right communication among the different PLCs. It will not start, for instance, if we have started a peroxide disinfection mode of the HVAC. These are common sense criteria. As I have already explained, one of the most difficult part of this is how we are going to qualify it. For that, what we did is approach of sequential steps, where we have two parameters. One of them is the flow step, and the other one is the stabilization time. So we determine a flow step equal for everyone, for every step. This is the percentage of fan speed that we reduce. And the stabilization time is the time we assure that all the parameters are under control. Then we have the minimum flow, which is from safety point of view, when we see that we don't have perturbances or that everything is stabilized and balanced. When we made this, in some cases, we find that we can go for a further minimum flow, but there are some occasionally some perturbances, so we decide to, in safety mode, to fix a minimum flow a bit higher than the one we can reach. Always we can reach a lower minimum flow, but we set one that is giving us enough assurance of safety for GMP purpose. And then we have the ramp time. This is also set a parameter of time, which also we fix it in a practical situation, where we reduce the time as much as possible, but minding that the pressure are not unstable for a long time. There's other parameters like the echo offset in terms of the two particles that we are measuring. We obviously don't fix the set on the regulation limits, on the ISO limits, but we give a safety margin here. So what is in green will be the eco mode working range, and the red part will be, let's say, the buffer we have to react and never be above the ISO limits. And as I said before, at the end of all the trials, we will have the minimum flow set and qualified. If we increase the flow step, I mean, if we reduce in every step a higher amount of air flow, the differential pressure of the different rooms will be compromised. If we reduce it, then the duration of the ramp down to the minimum flow will be longer, and the opportunity to save energy will be less. If we increase the stabilization time, also this ramp down will increase, and the opportunity to reduce costs will be lower. And if we reduce the stabilization time, the system stability will be lower. So during the startup and commissioning, important task, as I have said already several times, is to balance the right parameters, reaching the optimum ramp down time and minimum flow without compromising the 4 parameters: temperature, humidity, pressures, and particles. Same with the ramp up. If we increase the ramp up time, the pressure stability among the different rooms will decrease. If we decrease the ramp time, the clean room recovery will increase and will be probably a qualification matter issue. Mechanically, the system is everything conventional. I mean, we will count on the same EC fans in the air handling units. We will have motorized dampers in the supply. We need it. We will have the typical and conventional return dampers motorized, and we will have obviously the differential pressure transmitters. We will have the particle counters, as many as the risk assessment determine, with their isokinetic probes, their centralized vacuum, and the dedicated PLC. Regarding PLC, regarding control system, we have the PLC for the airborne particle counters. We will have the PLC for the HVAC. We will have the common system to control everything related to the clean rooms, as can be HMI in the clean rooms to see the different parameters: particles, pressure, temperature, humidity, whatever. We'll have also interlocks, or if the facility is provided with door open detectors, it will be here also in the CP clean rooms. And obviously, this will be connected to BMS or EMS, the central BMS or EMS of the facility. Obviously, everything GAMP 5 and 21st CFR Part 11. That is obvious. Taking the risk of repeating myself again, but I think that it is the hottest discussion on this approach, is how we are qualifying the system. We have a system designed to work as conventional, as in a conventional engineering. I mean, the air handling units and the ducting and everything will be similar to a conventional. We are not here reducing the capex. We are just engineering the system as if it will be commanded in a conventional way. But we are providing let's say a solution that can reduce the operating cost. So how do we qualify this? We qualify as conventional criteria, or shall we qualify it as the minimum flow rate? Well, first, as I said before, we have this commissioning phase where all these parameters, although we have the initial data from the engineering, but are confirmed during the practical commissioning. So normally in the startup, we will correct whatever deviation or whatever perturbances happens by affecting or or adapting the flow step or the stabilization time or the ramp up. We will, during qualification, obviously, once we set the flow step and stabilization, we will have verifications of 12 hours within limits, and then we will make some excursions of the parameters, temperature, humidity, or particles, to see what is the capacity to recover the room. And then finally, we will have a verification of the final minimum flow with this differential pressure stability. This obviously will take longer than the commissioning of a conventional system, and probably it will take 2 times more. Well, also it depends on how you establish the resources or the shifts to work in the commissioning. For the qualification part, we made the risk analysis on the critical quality attributes, which is the particle count, the microbial concentration, and the recovery time, and which are the critical process parameters that affecting to these attributes. So considering the HEPA filter integrity, conclusion is that the scenario where HEPA filter integrity is more compromised is in a conventional scenario. In eco mode, we will have lower flow and the integrity of the filter risk will be lower. If we talk about the differential pressure, conclusion is that we have to check the differential pressure at the different scenarios, not at the conventional, not at the minimum flow, but on both and the transition periods. When we are talking about particle concentration rates, the worst scenario will be the minimum flow. And when we are talking about air change rate, we think that we have to check it in the both scenarios, in the conventional, in also minimum flow. And the microbial concentration has to be verified at any flow. So as a summary, these were very brief explanation of Ishikawa diagram, but as general, I will say that HEPA filter integrity, obviously in a conventional scenario, will be at the design flow. In a smart clean room, will be at the design flow, also in a conventional scenario. For room differential pressure, we will have to make tests and qualify in both scenarios. Particle concentration at rest, we will test it at the minimum airflow at the eco mode. The air change rate, although it may be informative, but we will test it at the both scenarios. Air visualization and smoke test, we will make it. I think conclusion was the more critical is the worst, and the worst case will be the minimum airflow and the eco mode. Recovery time verification also at the eco mode, initial microbial count at the eco mode, and temperature and humidity and at the eco mode. This obviously has to be joined work with the user quality department, and there might be some debates, but it's only a matter of fixing what is the scope of the qualification. Well, we made a case study this case study is related to a facility that we made. It's a septic filling facility. It was a greenfield. The sterile area is only 140 square meters, but although there is a main air handling unit serving to this area, there was another 4 air handling units on the boundary affected by this one. Our very briefly, conclusion is that the eco minimum flow with all the safeties taken could be reduced easily by 44%. We reduce it much more than that, but in a safety, let's say, consideration and agreement with the client, we set it with reducing and to the conventional scenario of 44%, which is no less. Here in this diagram on the left, you can see different points regarding different tests we made at different velocities, fan velocities. You can see here an example of one of the days where we were working already in eco mode. There were some people making SAT in one of the equipment in the field machine, and the system reacted. Didn't need to reach exactly the conventional mode, but the system reacted to correct these excursions of particles. We never, in that example, we never reached the limit. We have here that under a smart Cleanroom, we were consuming 1.96 kilowatts per hour. In a conventional mode, we were consuming 8.5 kilowatts per hour. And in intermediate mode, we were consuming around 3 to 5.5 kilowatts per hour. We are now going to show some other diagrams of tests we made. So what you can see here, the red line are the GMP limit. Cubic feet meter, please. Then the yellow one is and the smart Cleanroom limit, the one that we put as a reaction time. I mean reaction criteria for particles. The green line is the flow rate that we were given to the system. And the purple one is the particles counting, particles 0.5 microns. So as you can see, we started in the left with above around 19,000 cubic meters per hour. We reduced it to less than 11 in the eco mode. Then we force an excursion of particles very, very, very high. This was an artificial force. We pour it. The system reacted immediately, and the particles counted were reduced almost immediately. And we are talking here probably about less than 1 minute of excursion and reaction. You can see the green line goes up immediately to the conventional mode, and then stabilize there and see that all the parameters are already in accordance to the set points, and go again to the eco mode. That test was made also with a different concentration of 5 microns particles, and the system will have not reacted because we never reached the yellow line. The system reacted because in the 0.5 microns, it was above the yellow one. We made same test with a different concentration of the biggest particles, and well, probably here it was a bit longer to recover, but also we are talking about 2-3 minutes to recover the situation. Compared to a conventional system where probably the particles counting are separate to the HVAC control, you will have probably not detected or not reacted. probably you will have also had this peak over here, and I don't know if it will remain longer or not. But what we conclusion was that the system was very safe, and that the reaction time and the recovery of conditions were also very quick and satisfactory. At the end of the day, what we evaluated in these case studies, the fan electrical consumption was reduced up to 77%. That the HEPA filters replacement, we could evaluate, this was an estimation together with I think it was Canfield, up to 29% of reduction of cost, and black utilities will reduce also 54% of cost. Black utilities will depend very much on the placement and on the strategy of the HVAC. Obviously, if we are talking about 100% fresh air, the opportunity to have a cost reduction of energy consumption is bigger than if we have a 10% of fresh air. If we have a location where high temperatures or humidity, also the savings opportunities are much bigger. These percentages, if we bring it to euros, let's say, the HVAC fan, you can see here that we can be saving in a year like 70,000 euros, but in the black utilities, saving could be more than 100,000 euros for this small facility. Well, and finally, can I implement a smart clean room in my factory? Obviously, if you have the will to do, you can do it. If you are talking about a greenfield, the implementation of smart clean rooms have to be considered, obviously, from the early stages. Cannot be considered at the early stages of the detailed design or during construction. Has to be established during the basic, even conceptual design. It will require, obviously, risk analysis on HVAC, on APC, and on the smart clean room. APC, I mean, the air particles counters will have anyway risk analysis, because you have to determine with or without a smart clean room where you want to locate the particle counters. And then we will have the smart clean room analysis. We'll have engineering and construction services to develop and execute the construction, and obviously the engineering services for the commission and qualification of the whole system. If you are talking about from brownfield, probably the return of investment is not that quick, because you may need to change things that you were not planning to change. In a greenfield, anyway, you have to enact it from the beginning. So mainly the additional costs in a greenfield are not that big. If we are talking about aseptic areas or sterile areas where most of it are class B, also the investment, additional investment is not that big, because the particle counters has to be there anyway. If we are talking about class C or class D areas, then the smart clean room requires to install particle counters where in a conventional scenario you will not consider, and then the investment will be bigger. Now, in a brownfield, it will require a preliminary feasibility study before taking decision to go further or not, because we may face situations where the changes in the HVAC system, air ducting or even air handling units are major, and that will require investment or shutdowns that you are not planning with. So we need to make a preliminary feasibility study of the installation, data acquired, and survey of the current installations, but also the hardware and software. We may have to adapt also the BMS or EMS or even the PLCs of the existing facilities. We will have to make obviously the particle count risk analysis. We will make the return of investment after having these assessments, and then we will start with engineering services. So yes, you can implement this kind of solutions in your facilities. Obviously requires a calm debate and discussion with not only operations but engineering and obviously the quality control departments to align of what we are doing and to be conscious of the change. At the end of the day, the facility will have more data, more centralized, and whatever deviation or excursion will be better reported. So I don't know if I went very quick, but I think this is all that we can say in such a short time. Now is time for whatever questions you may have. And so I'm open to you. Please go ahead.
So Salvador, firstly, thank you very much. Do we have Salvador live? Him on the line. Salvador, hello.
Hello.
From me, thank you very much for your contribution to the conference today. Extra appreciation also that you spoke in English. So that helped our understanding. I appreciate your language change for this morning. We have a couple of questions that came in through the app. So I'll ask those on behalf of the virtual audience. The first question, Salvador, is that you spoke of an active VAV, an active variable air volume system, which includes room pressure control. And the question is, how do you prevent the room pressure from responding to open doors, leading to unstable pressures?
Well, this problem also happen in conventional setup. Whether you have a constant air volume in the supplies, the opening doors will always create a perturbance of the differential pressure among the different rooms. You have quick reaction systems in the returns, like the BAV. It's not coming to me the name now, sorry. But also the doors opening signals can help you through the BMS to react quickly on this, to freeze the situation where the supply was and to correct. Obviously, doors opening will always equal the pressure in the two rooms. And this is a situation that will always happen.
Did we hear you also, Salvador, mention detectors, door open detectors in your presentation? Yes. So if a door detector triggers, then perhaps that doesn't then try to hunt and change the
you can react quickly. You can, okay. Yes.
Understand. Thank you. I'll look to the room. Is there anybody in the room who would have a question for Salvador? Connor? Yes. If you ask the question, I'll repeat it then for you, Salvador, and the virtual audience.
The question relates to how they correlated the environmental monitoring data on viables in the different conditions, and were there differences between the design flow rates and the eco mode? Were there any significant differences in the income setup rates, active air samples, etc.?
So the question, Salvador, is from Connor Murray, and the question relates to your total airborne or non-viable particle counting and the viable microbial burden on the room with your control software, your smart clean room in the eco mode or the conventional mode. does it take account or give any consideration to the microbial counts in the room or the microbial limits of the GMPs?
This is a good point, and indeed is the following step of our development. We have tested only with the airborne particles counters, conventional. Well, next phase will be also to test it with the non-airborne particles systems. Question we had here when we started with this was 3 years back, and the information we had about the non-airborne particles counters were that stability of the measurements were not very big, and well, we decided to start with the airborne particles only. Next step will be.
There was a comment on virtually, Salvador, from Vicky Tickle said, I like the idea, but it would worry me that moving away from a good buffer, i.e. operating well within established limits. It might be just my lack of engineering knowledge, though I am a microbiologist. So I think Connor's question is a common one on all of our minds in the GMP life science healthcare industry, that real-time particle counting, total airborne particle concentrations are available, but real-time rapid micro methods are not in a monitoring system sense. But that is the reason for the pharmaceutical healthcare life science clean room. So I think there is still some concern, but it's blazing a new trail for sure. Connor has perhaps a follow-up.
Sorry, my question was more focused on when the EM data for vials was qualified at the design and then separately at the eco position. On the trending data, was there any significant change? Because the trend is your friend in EM monitoring and vials. So was there any significant difference between the EM data at the design flow rates and the eco flow rates?
Right. So
case study to try and give some comfort, like to Vicky,
yeah.
that when you're in the eco mode, the trending and the baselines are not significantly different, or are they different?
So whilst perhaps, Salvador, not monitoring microbiological counts, was there any change that you noticed or studied in this or any other case study for the difference you might have seen in the baseline for EM data on microbiological counts in your eco setting or your conventional setting? So did you see any trend changes in the microbiology of the room?
Yeah, that's my question.
No, really. We in this case with this client, we let's say put this in this case put the system on, qualified, and have some track on microbiology, but was not a long trend. A long trend. They finally decided not to take the eco mode for conventional for the current situation. So they went on with the conventional mode, and we didn't have the track of the macro. But as I said, this is the following step that we are considering to develop.
And I think to what you have spoken to in the presentation before you, Salvador, one of the questions relates to the appetite, clear appetite for carbon emission reductions and for energy saving. There's a real appetite for that, but also a trepidation, a risk, a concern. And in between that is the regulator. In the industry, we're talking here about GMP industry, there is a regulator. Do you have any experience with your local regulators of how this has landed with them, how they are accepting or talking with your clients about this type of approach?
Well, I think we are positive on this. Mind that the approach that we have made is not, let's say, exactly variable change system with no control limits, so we have made a hybrid system where you have really two positions where the system is working. One is the conventional, which is the conventional one, no issue, and the other one is with a low energy consumption, but assessing that we are within the limits by far in particle counters, airborne. This is the matter.
Yeah.
So we need to resolve the micro part, the non-airborne particles, to have a further interaction with the authorities. But initially they saw the approach correctly, with a risk assessment correctly in place, and with two positions of, let's say, working.
Okay, thank you, Salvador. I'm looking to the room to see if there are any final questions. If not, we're on our time. Salvador, I'd like to extend a final thank you to you, and for anybody in the room or virtually, if there are any follow-on questions, please do put them into the app or on email, and I'm sure Salvador would be happy to continue that dialogue. Very interesting, Salvador. It's a brave world that you're stepping into, and I think that it's wanted, it's required, it's exciting, but it's also going to carry some challenge too. So good luck, and thank you again from us here in the UK.
Thank you.
Thank you.